Gamma distributions are generally used for estimating waiting times, for example, when mechanical parts fail. It's also useful in other areas of inquiry such as science and econometrics. Gamma PDFs are continuous, unbound right-skewed distributions that cannot be less than 0. Its right tail is longer than the beta's PDF, but shorter than the log normal's PDF. The formula for calculating its two shape parameters, alpha and beta, are simpler than the log normal 3-point or LSS methods, where gamma's alpha and beta are calculated from mean and variance. The mean and variance needed to calculate gamma are either from observed data or the results of beta or triangle distributions using a min, most likely max input method. Here is an example of the formulas used in Excel, where probability is greater than 0 and less than 1. Alpha and beta are shape parameters. Cumulative of true yields a cumulative probability distribution, and false yields a mass density distribution. To the left, we'll use again the same example as in our previous video, where we're going to look at the sand grain size distributions, which are limited between 60 and 2,000 microns, and our sample has a most likely or mode value of 500 microns. When we examine the PDF curves, we can see that the log normal distribution in blue has a much longer tail than the gamma in brown. The triangle in red and beta distributions in black are also restricted to the bounded nature of our distribution. The results of our analysis are also summarized in the descriptive statistics table on the lower left. Note how the max for the gamma and log normal exceed the 2,000 micron limit for sand. Also, the minimum for the gamma is less than our 60 micron limit. Now, let's move on to our Excel demonstration. Looking at our sandstone grain size analysis again, it's clear that we wouldn't want to use the log normal or the gamma because their tails extend beyond the limit of 2,000 microns that define sand. So we'd either want to use the triangle in red or the beta in black. But I do have an example here where we can look at where you would want to use a gamma distribution. The city with daily electric power consumption in million kilowatt hours is a random variable x having a gamma distribution with the mean of 6 and a variance of 12. And we want to know what is the probability that the number of kilowatt hours is between 4 and 8 kilowatt hours. So I've input 6 and 12 kilowatt hours as the mean and variance of what we were able to observe and calculated the alpha and beta. And then using the gamma dist function, we've calculated the probability of 4 kilowatt hours at 0.32 and 8 at 0.76. And the difference between the two is the probability of kilowatt hours ranging from 4 to 8. I've also demonstrated it here on a cumulative probability chart where I've just calculated the gamma in and gamma dist functions with a cumulative of true. As with our previous spreadsheets, I've done the same thing where I put my inputs at the top. I have my results statistics in the table. Down below here, I calculate mu and sigma for the 3-point, and that's used for the log normal. And on the far right is where I've calculated the gamma distribution using gamma inv, where we use some probability and then alpha and beta. We also do likewise for the log normal, the beta, and we use our special formula for the triangle, which is quite a long formula. Then we have our table for plotting our curves, our frequency distributions, and again, some write-up on how to do these types of analysis. If you want to play around with this worksheet, I'll leave a link in the video description. Thanks for listening, like and subscribe.